we're going to finish up the last little bit of chapter 2. So impulse. Impulse is not the impulse to go shopping. Impulse in physics is going to be a force that's acting on an object for a period of time, which we're going to call lowercase t. So an impulse produces a change in momentum. You apply a force over a period of time and momentum will occur. But there's also another example of impulse, which I think is a little bit more tangible for us to understand. And that's if you have, oh no, this glass and it's full of red wine and it's going to stain everything. But you also don't want to break the glass. Say it's your favorite glass ever, your grandmother's glass you've inherited, and you have a carpet on one side and tile on the other, and you had to predict which would you rather the object fall on it, not because of the stain of the liquid, but because you don't want to break the glass. Well, you're likely to say, well, the carpet has the best shot of the glass not breaking. If it hits the tile, it's most certainly going to break. But the carpet, it may not. And the reason why is because of impulse. If an object is dropping and it's hitting the floor, the carpet is going to absorb the force of the object over a longer period of time, whereas the tile is just going to hit the ground in a single instance with a large amount of force. It's the same reason why hitting a hay bale versus hitting a concrete wall might feel different in a car. Some other examples are airbags. It absorbs the force of your face, which is better when you hit the steering wheel than just hitting the steering wheel straight on with nothing to absorb that force. You're padding for your elbows and knees, so even though when you hit the ground, it's still going to hurt, but it means your elbow and your knee aren't making instant impact with the ground. There's something to absorb the shock. And then also protective plastic barrels on the highway. These tend to be at exits when you're getting on and off the interstate or along guardrails sometimes, but they help absorb the shock. And that's impulse. You're making the force over a longer period of time instead of a short period of time. And that's usually safer. So now let's talk about forces in circular motion. So circular motion is accelerated motion, remember, because we have speeding up, slowing down, or changing direction, or both. So because you're going in a circle, you're technically accelerating. We have a figure down here to help us understand the difference. So centripetal acceleration must be present. And centripetal acceleration is almost like and centripetal force is almost like, it's called a center-seeking force. It's what holds you in the circle that you're traveling. Without the centripetal force, you wouldn't be able to travel in a circle. It's the same thing that if you were to take a yo-yo on a string and spin it around, round, you're the pinpoint source, but you're where the center is. And the yo-yo is seeking that center, and that's the direction of the force. If you were to let go of the yo-yo, what happens is the yo-yo is going to swing off in a straight line. And the same thing would happen is if you were traveling in a circle and all of a sudden the center-seeking force was gone, your car would fly out in a straight line away from the path you were on. Now there is another type of force that we feel, which is called the centrifugal force, which is on the left-hand side of the image. It's the force that makes you feel like you're going to pull out of the circle. So if you've ever traveled around a really tight curve, you kind of feel like your body's being pulled out away from the center of the curve, the part that you're going into. And that's the centrifugal force. It's the apparent outward tug of the direction change. You can kind of feel it when you're going around, like turning left and right in a car or going on a bike, maybe. You have to be going kind of fast. But that's the opposite of centripetal. The centripetal force is pointing in towards the center, keeping you on that circular path, whereas the centrifugal force is the outward tug that you feel. So Newton's law of gravitation, this is the one we said he was working on at the same time that he was working on his 3 laws of motion. And what his law of gravitation says is that there's an attractive force between all masses, and that the force is proportional to the product of the masses. So as the objects get bigger and heavier, the force gets bigger. So something like the Earth and the moon have a gravitational force. Something like the Earth and the sun have a gravitational force. And so the other part of it is that there's a distance factor. And this is kind of similar to magnets. You know, when you have two magnets far apart, that there's no attraction between the magnets. They almost don't know that each other exists. But as you get the magnets go closer together, eventually the magnets are going to smack together because all of a sudden the force is great between the two magnets. And the bigger the magnets, the bigger the force. So as two objects get further apart, the force decreases. And as the objects get closer, the force increases, which is why the sun, the moon and the earth have a very strong gravitational force. And the presence of the moon actually changes our tides. It causes the ocean to bulge out in some places and to recess in other places. So it has impacts on tides, and we'll see that when we get to earth science. And the other thing is that this provides centripetal force for orbital motion, right? So if you think about the moon like a yo-yo and the earth like your fingers, the earth traveling the moon traveling around, round, is seeking the earth. That's the center seeking force. Now, if that was to be gone, the moon would travel out in a straight line path motion out into space. So it's really important. It holds this this Earth-Moon relationship together, which is important for a lot of reasons to our world. So weightlessness. We talked a little bit about weightlessness when we discussed the traveling in the elevator. And so weightlessness is a really specific thing. We also talked about it when we talked about skydiving. So skydivers and astronauts are two different types of ways in which you might experience apparent weightlessness. You feel weightless, but you still have mass, so you're not truly weightless. But in this time, it's because the objects are in free fall acceleration with a force of g. So to experience true weightlessness, one would have to travel really far from Earth and its gravitational field, and far from gravitational fields of other planets. You have moments of weightlessness where you might be on a roller coaster going down. If you've ever stepped off a curb when you didn't know that you were going to step off the curb or a step, you have a period of time where your stomach goes up into your throat and you kind of feel weightless for that brief moment. Elevators can kind of get closer to that. And so those are examples of weightlessness, but you don't have no weight. You just are free falling with an acceleration of g, which takes into account the gravity. So those are all of our slides for chapter 2. So you finish it up, make sure you complete all of your notes and submit them where you are supposed to.